Hey Panthers, it is Dr. Augustine. How are you doing? We are going to attempt number 3 to record the last lecture of the year. If you ever wondered if I like you guys, this is proof. I just spent an hour. What in the world just happened? I just spent an hour recording a lecture that didn't actually show the PowerPoints, but you got to hear me speaking for an hour. And I hope this one works because it is now 7:30 on Thursday night after your exam. I tried doing this yesterday and I had computer problems. I spent an hour on the phone with IT, and then I did it after Learning Lab. I did it. I've not eaten dinner, so do not let it be said I don't like you guys. Love you guys. All right. Let's finish up chapter 10 here. We're going to talk about valence bond theory and hybridization theory. And I want you to think about the idea that we have learned how to write Lewis structures. Pen would probably help here. Lewis structures. Wow, what is that wind sitting there? I don't know if you guys can see that or not. And we've learned Vsepr. Those are both models of chemical bonding. All right, now I know most kids don't play with models or build models anymore, but when I was a kid, I used to build models. And they were mostly model cars and model airplanes. Those were the kind of things I was interested in. And what do you want when you build a model? I mean, what are you looking for in a good model? So a good model should represent whatever it is that you're trying to make. Let's say we're trying to make a car. You want 4 wheels on the car. You want a steering wheel. You might want to see the engine. You might want maybe a convertible top or something. You want something cool about the car, maybe a Corvette or something. So a good model has to have the properties of whatever the thing is that you're trying to make, but can't be so complicated that it ends up being the thing that you're making. Like, when I was building model cars, they weren't actual cars. They were plastic representations of the car. And depending on how much money you spent and how much time you wanted to spend and how careful you were, you could buy models that were better. So some models just sort of show you, yeah, this is what a Corvette looks like. I don't know if any of you have ever seen a Matchbox car. That shows you what the car looks like, but this can't usually do much. I mean, maybe some of the better ones, the hood can open up or the doors can open or something, but they don't do that much. If you get a better model and you're careful when you build it, you can actually get ones where you can turn the steering wheel and the front wheels will turn, or the doors will open up and you can see the inside of what it looks like, or the engine will have a bunch of details in it, or maybe if you have a convertible, you can actually open and close the convertible. I mean, that's a pretty nice model. So as you spend more money, as you get more sophisticated, the model can be more and more representative of the thing that you're trying to make. But it's always limited. It's a model, right? It's not the actual thing itself. So if we want to understand chemical bonding, we can start with a very simple model like a Lewis structure. A Lewis structure tells us, hey, if I have this molecule right here, I have 2 hydrogens and 1 carbon attached to a central atom, and there's double bonds to the oxygen, there's single bonds to the hydrogen, there's lone pairs on the oxygen. So all that stuff's great, right? I mean, all that gives you information about the chemical bonding environment. In other words, it tells you what's attached to the carbons, what's attached to the hydrogens. Now this one, in this case, there's only 4 atoms, but you could have a much more complicated molecule. Maybe something like that. Okay? And then as long as you're not violating the octet rule, that molecule really exists. That's what all of organic chemistry is about, trying to understand these different molecules. There's different ways to name them, the reactivity is different, all that other stuff. But a Lewis structure gives you that. Okay, and if you follow the rules of writing a good Lewis structure, you can understand what things are attached to what. Now the limitation of a Lewis structure is kind of illustrated right here. Oops, sorry. Kind of illustrated right here. That carbon, so I can erase the mess I made. That carbon right here is attached to hydrogen plus another carbon plus another oxygen. But if all we have is the Lewis structure, we might conclude this is a 90-degree angle. But you already know that's not the case. So that's how we introduced this Vsepr model. So the Vsepr model lets us predict what's the shape of the molecule. And it does a very, very good job. It tells you, hey, this is actually attached to 3 different electron groups. Therefore, these are actually 120 degrees apart. This is actually called trigonal planar. This guy right here, well, that's attached to 4 groups. That's actually 109.5 degrees. And this one's actually called tetrahedral. Okay? So Vsepr model takes a simple Lewis structure, which is, we teach that in high school. We add onto it one layer of complexity, which is count the number of electron groups around the central atom, and that allows you to predict the geometry. It even allows you to do stuff like realize, hey, water, that's actually less than 109.5. Why is it less than that? Well, these lone pairs there push that bond down a little bit closer. So it even allows us to predict some things that we observe in nature, that the angle between H2O is not exactly 120 degrees, or excuse me, 109.5 degrees. All right, good model. But the model begins to break down when we start looking at things a little more carefully. So let's take a look at this molecule compared to this molecule. Okay, we know that both of these exist. That's fluorine, that's a gas. This is hydrogen, that's a gas. If we look at the Lewis structures, I have no idea where the whole win is showing up there. If we look at the Lewis structures, we say that's got a single bond, that's got a single bond. It's a covalent bond. They're both non-metals. So these should basically be the same, right? It's hydrogen and fluorine. They both are basically the same thing. But it turns out in reality, this one's about 430 kilojoules per mole and about 74 picometers. That's the strength of that bond, that's the bond association energy, and the length of that bond, the equilibrium bond length, is about 74 picometers. This guy is approximately 150. What just happened here? Sorry guys. This one's 150 kilojoules per mole, and it's about 120 picometers. All right. So the Vsepr model has failed us in a very important way. And it's failed us in the following way. I've lost my tools here, sorry. There we go. It's failed us in the following way. It does not even begin to get the energies right. Right? The energy of these, they're off by about a factor of 3. The bond length is significantly different in these two things. And Vsepr model tells us nothing about those two things. It tells us nothing about that problem that exists. Okay? So, I want a model that's better. I want a model that's going to predict why this is happening. Why is a hydrogen-hydrogen bond 3 times stronger than fluorine-fluorine bond? That's where valence band theory comes in. It was introduced in the 1930s to try to explain some of these discrepancies that people were starting to measure. All right, so let's think about what's going on here with the electrons. So the idea behind the valence band theory is a covalent bond is more stable by sharing electrons. So sharing electrons makes the material or makes the molecule more stable. And the way it does that is by getting a filled shell configuration. We already kind of knew that from the Lewis structures. So if we think about that, each hydrogen has a 1s electron. I'm going to write them up and down, 1s1, 1s1. That's each hydrogen. When these guys come together, they can combine and share with one another to fill their orbitals. So we can make a chemical bond by sharing one electron between each of those guys, and that will stabilize the molecule and it will fill the shell. So if you want to think of it from a sort of picture of where the electrons are, remember an s orbital is spherical. So these guys come near to each other, they can overlap with one another, the electrons can overlap in between the two molecules and form this new stable chemical bond. So we would call this a 1s, 1s covalent bond. That's the covalent bond that's formed between the two hydrogen atoms. Contrast this with fluorine. So fluorine has an electron configuration of 2s2, 2p5. So that's going to look something like this. Each one looks like that. All right? So there's one extra slot looking for an electron to be formed, but each one has one slot that can share with the other. So this one, we end up with something like, whoops, something that looks sort of like this. This is one of the fluorines. This is the other fluorine. It's got a p orbital with an extra electron in it, and this guy's got a p orbital with an extra electron. I'm purposely drawing one upside down, one right side up. So where those two orbitals overlap with that extra electron, that allows the formation of a chemical bond. So we would call this a 2p, 2p bond, covalent bond. All right, so this begins to explain these numbers up here, because s orbitals, what this is telling us is s orbitals form stronger bonds than p orbitals. That explains the factor of 3 difference. Also, in order for two s orbitals to overlap, they've got to be closer to one another. That explains the shorter bond length. So those two s orbitals have to physically be closer to one another in order to share those electrons between them and form a chemical bond. All right? So valence bond theory tells us, hey, every time we have an s orbital interacting with another orbital, we should expect a little bit shorter chemical bond. All right, that explains a few very simple molecules like hydrogen, fluorine, HF we can use explaining this way. But unfortunately, most of the other molecules we could draw are not going to be explained by this. They're going to need a little bit more complicated thing. And we need to introduce a concept called hybridization of orbitals. Let me illustrate to you the problem then. So let's take beryllium dihydride as my example. All right, the Lewis structure for this, remember this is one of the molecules that can violate the octet rule. 2 hydrogens attached to a central beryllium. Now, beryllium, the electron configuration of the atom, looks something like this. 2s2, 2p0. Okay, there's no electrons in the p orbitals. So, where's the sharing going to come from? I mean, there's empty slots in here, but there's no sharing of electrons. Remember I said that valence bond theory says sharing electrons leads to stability. Well, there's no electrons to share in the p orbitals. The other problem with this, you might say, okay, well, yeah, but the hydrogens, there's 2 hydrogens, and each one of them has an electron, so maybe that can share some electrons. Okay, but there's nothing to match up with it. But even if that were true, p orbitals look like this. One along the x-axis, one along the y-axis, one along the z-axis. Okay, remember they're 90 degrees apart from each other. There's 3 of them. So if this was somehow some interaction between a hydrogen and one of these empty p orbitals, we might hang one of the hydrogens off one side, hang one off another side, and this would predict that the bond angle between these should be 90 degrees. But in fact, when we do the experiment, when we measure it, it's actually 180 degrees. So we got a problem. If we just use the atomic orbitals and where we know the atomic orbitals are, we do not end up with 180 degree bonding. We end up with 90-degree bonding. And the additional problem is we have no electrons to share from the beryllium. It's got 2 electrons, but they're already paired up. All right, so how do we get around this? We do what's called hybridization. All right, so I'm going to do something for you here, which you might appreciate. I'm going to give you the answer to a whole bunch of questions that you might encounter and not explain why. And I'm going to stop that video and save it as part 1. So if all you want to know is the answer to some questions, watch the next 10 minutes. You'll be able to answer some questions. You can go on your merry way. If you want to be able to answer all the questions, you're going to need to hang in there and watch another 30 minutes explaining the details of hybridization. All right? So let's do how to answer some questions. All right. How do we determine the hybridization state? So I'm going to skip ahead. We're not even going to talk about hybridization, what it is, and I'm just going to tell you the answer. So the way we do this is we start with a molecular formula. Let's take CH4 as an example. Then we write the Lewis structure. Carbon attached to 4 hydrogens. Or let's take CO2 as another example. I'm picking examples we've done before. Okay, that's the Lewis structure for CO2. From the Lewis structure, we count electron groups. We count electron groups around the central atom. This guy has 4 groups. This guy has 2 groups. You might be saying, well, wait a minute, those are double bonds. Remember, a double bond counts as 1 electron group, 1 region of electron density. All right, so this one has 2 groups. This one has 4 groups. And from the number of electron groups, maybe I'll give you one more example to show you another situation. Let's take NH3 as an example. The reason why I picked this is this one has a lone pair around the central atom. So that one has 1, 2, 3, 4 groups again. So remember, we count the lone pairs. All right, so this one has 4 groups also. All right, so once we count the number of electron groups from the Lewis structure, then we can figure out what are called the electron group geometry. Okay, I call them electron domains in class also. 4 groups, tetrahedral, remember? 2 groups, linear. This one's tetrahedral. This is the electron group geometry. Electron group geometry, not the molecular geometry. Remember, ammonia, the molecular geometry is different. If you have lone pairs, it's going to be a different name. That one turns out to be trigonal pyramid. Okay? So how is that helpful? And then you may have been asking yourselves, why is he making a deal out of this electron group geometry? The reason is, from the electron group geometry, we can predict hybridization. Okay? That's what allows me to tell what the hybridization is. That's why we specify what electron group geometry is. Tetrahedral turns out to be sp3. Linear turns out to be sp. So here's how the whole table works. 2 groups, 3 groups, 4 groups, 5 groups, 6 groups. So I'm going to give you the groups, the electron group geometry, and the hybridization. Okay, so 2 groups is called linear, 180 degrees. Hybridization is sp hybrid. 3 groups, trigonal planar. sp2, remember this is 120 degrees. 4 groups, tetrahedral, 109.5. That one's sp3 hybrid. 5 groups is called trigonal bipyramid. And remember, there's actually 2 angles in this. There's 120 and there's a 90. That one is sp3d. 6 is octahedral. These are all 90. and that one's sp3d2. All right, that's the answer to one set of questions. Okay, you're taking a test, you're given a molecule. The molecule looks something like this. Actually, I'm going to draw it just as a Lewis structure. Molecule looks something like that. The question is, what is the hybridization on the carbon? You just count electron domains, 1, 2, 3 electron domains. Therefore, the hybridization is sp2 hybridized. You can actually do this for the oxygen too. It's got 1, 2, 3 domains there. That's also sp2 hybrid. Okay, I haven't explained what sp2 hybrid means. I'm just telling you the answer to a certain question you might get. What's the hybridization on this atom? You write the Lewis structure, you count the number of electron domains, and then you just memorize this little table right here. That'll tell you not only the geometry, the electron group geometry, it'll also tell you the hybridization. And that's why we made a difference, a distinction between electron group geometry. All right, I'm going to give you the answer to another set of questions which you might get. Here's a relatively simple carbon molecule with two bonds, with a double bond in it. And another question you might get is, how many pi bonds, how many sigma bonds, and how many pi bonds? All right, how do we answer that question? Well, one single bond equals one sigma bond. One double bond equals one sigma and one pi. And one triple bond equals one sigma, two pi bonds. All right, so in the molecule above, 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. Okay, haven't told you what a sigma bond is, haven't told you what a pi bond is. I'm just telling you the answer to some questions you might encounter. You might encounter a molecule with a bunch of different bonds on it, and you got to count up how many sigma bonds and how many pi bonds. Okay, so I'm going to give you one kind of crazy looking molecule. I'm just going to make something up. No idea what the name of this is. Definitely need a nitrogen in here. Need some more bonds over here, don't I? Alright, lone pairs and everything. That oxygen needs a lone pair too. We're going to make the octets work out. Alright, and you might be wondering, well, how do you know this is right and everything? Okay, I've been doing this for a while. Alright, but it's not right. I'm actually violating the octet rule in two places. So this guy needs another hydrogen, and this guy needs another hydrogen. Now I'm not violating the octet rule, I don't think. Look over here, this guy's got 4 bonds, that guy's got 4, 4, 4, 4, 4, 4, 1, 2, 3, 4, 4. Okay, we're good now. Have to add some hydrogen there to fill everything out. All right, so that's kind of a crazy, ridiculous looking molecule, right? So the question is, how many sigma bonds and how many pi bonds? You might want to pause the video right now, see if you can answer this question. Sigma bonds, pi bonds. All right, sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 sigma bonds. And 1, 2, 3, 4. 4 pi bonds. How did I do that? I just count every single connection between every atom. That's a sigma bond. And then if there's a double bond, it counts for 1 pi bond. If there's a triple bond, it counts for 2. All right, that's all there is to it. Don't forget, this guy actually contains 3 bonds, a sigma and 2 pi's. That's the only trick with this. All right, so here's a good place to stop. If you just want to answer some questions, the questions you want to answer are, hey, wait, actually, let's do one more thing with this molecule since I've already got this written out here. Let's call this carbon 1, carbon 2, carbon 3, 4, 5, 6, 7, and let's call this oxygen A, oxygen B, and there's only 1 nitrogen on there. All right, let me just ask a couple of questions then. Tell me what the hybridization and geometry is on carbon 3. You want to stop the video, take a look at it, and see if you can answer that. Hybridization on carbon 3. Carbon 3 has 2 electron domains. That means it's linear, and that means it's sp hybrid. So is carbon 4, by the way. Carbon 5, take a look at that one. All right, that one has 3 domains, 3 regions. Trigonal planar, must be sp2. How about carbon 1? Carbon 1, 4, tetrahedral, sp3. Oxygen B. Tricky. 1, 2, 3, 4. Remember, the lone pairs count as electron groups, so that's got 4. It's also tetrahedral, also sp3. Oxygen A is 3. Trigonal planar, sp2. And how about that nitrogen up there? That one's got 4. Tetrahedral, sp3. All right, if you want to stop the video right now, this will give you the answer to a bunch of questions you might potentially get. Here's a molecule, what's the hybridization? Here's the molecule, how many sigma bonds, how many pi bonds? Here's the molecule, what's the geometry? What's the bond angle, etc., etc., etc. All those questions we now have the tools to answer. The things we don't have the tools to answer are, how does hybridization work in bonding? And what is a sigma bond and what is a pi bond? I told you how to count them, but I haven't actually told you what they are. So if you want to watch that, you're going to have to watch the other video. It's going to take a little bit longer to develop. If all you want to know is the answer to some questions, and you say, hey, I'm willing to not know the answer to a few more questions, boom, you're done. All right, let's see if we can stop this video. This is always a trick here. So we can stop the recording, and then I'll record video number 2 in a minute.